When feeding a panel from a 120/208 volt service, you will generally need to use a 4-wire system, which incorporates a separate neutral and ground conductor. This configuration is primarily based on the distinct functions served by the neutral and ground conductors. The neutral conductor's purpose is to carry the return current for the electrical circuit. It is typically connected to the center tap of the transformer that supplies the service. The ground conductor, conversely, provides a low impedance path for fault currents, enabling them to flow back to the source, thereby facilitating the operation of overcurrent protective devices like circuit breakers. It is typically connected to the ground rod or other grounding electrode to the service entrance. Bonding the neutral and ground conductors together is permissible only in specific situations, such as when the service is supplied from a single-phase transformer with the grounded neutral. In situations where the service is not explicitly known to be supplied from a single-phase transformer, or if there is any uncertainty, it is safest to adhere to the 4-wire system with separate neutral and ground conductors. Therefore, you should run a 4-wire system from the meter stack to the panel, incorporating separate neutral and ground conductors. In addition to this, install a ground rod at the panel location and ensure the ground conductor is properly bonded to it. The specific requirements for grounding and bonding are meticulously detailed in Article 250 of the National Electrical Code, also known as the NEC. This article provides comprehensive guidelines for ensuring electrical safety by establishing a low impedance path for fault currents, reducing the risk of electrical shock, and minimizing voltage surges. Section 250.24 of the NEC addresses grounding requirements for alternating current systems and stipulates that the grounding electrode system must be connected to the system neutral of the service entrance. This connection is typically made at the main service disconnect. The grounding electrode system can consist of various elements, including a metal underground water pipe, a concrete encased electrode, a ground ring, or ground rods or pipes. Ground rods must meet specific requirements outlined in Section 250.52. A5, including being at least 8 feet in length and made of approved materials, such as copper or galvanized steel. The number and spacing of ground rods are also specified in this section to ensure effective grounding. Section 250.28 delves into the requirements for bonding jumpers, which are essential for ensuring electrical continuity and low impedance between different metal parts of the electrical system. Bonding jumpers are used to connect service equipment enclosures, metal raceways, and other metallic components to the grounding electrode system. These jumpers must be sized appropriately based on the size of the service entrance conductors as outlined in Table 250.102. C. 1 of the NEC. Section 250.30 provides guidelines for grounding separately derived alternating current systems such as those supplied by generators or transformers. In these systems, the neutral conductor must be grounded at the source and a bonding jumper must be installed between the source enclosure and the grounding electrode system. The size of the bonding jumper is determined by the size of the derived phase conductors, in accordance with Table 250.102. Seat 1. Section 250.32 addresses grounding requirements for buildings or structures supplied by a feeder or branch circuit. In these cases, a grounding electrode system must be installed at a separate building or structure, and it must be connected to the equipment grounding conductor of the feeder or branch circuit. The grounding electrode system can consist of the same elements as those used for service entrances, such as ground rods or a metal underground water pipe. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the feeder or branch circuit, as outlined in Table 250.122. These are some important sections of Article 250 of the NEC that provide guidance on grounding and bonding requirements. However, it is essential to consult the latest edition of the NEC and seek guidance from a qualified electrical professional to ensure compliance with all applicable codes and regulations. The role of a ground rod is to provide a direct connection to the earth, creating a low impedance path for fault currents to dissipate safely. This connection helps to stabilize the voltage to earth during normal operation and, more importantly, provides a path for fault currents to flow back to the source in the event of a ground fault. When a ground fault occurs, such as when a live conductor comes into contact with a grounded metal enclosure, the fault current will flow through the grounding system back to the source. This high current flow causes the overcurrent protective device, such as a circuit breaker or fuse, to trip, disconnecting the circuit and preventing electrical shock or fire hazards. A properly installed ground rod helps to ensure that the fault current is effectively dissipated, allowing the overcurrent protective device to operate quickly and reliably. The NEC specifies minimum requirements for ground rods, including their size, material, and installation depth. Typically, ground rods must be at least 8 feet long and made of copper or copper-clad steel. They must be driven into the ground until at least 8 feet of the rod is in contact with the earth. In areas with high soil resistivity, multiple ground rods may be required to achieve an adequate grounding resistance. The resistance to ground of a grounding electrode system is a crucial factor in determining its effectiveness. A lower resistance to ground indicates a better connection to the earth, allowing fault currents to dissipate more easily. The NEC recommends that the resistance to ground should not exceed 25 ohms. If the resistance exceeds this value, additional ground rods or other grounding electrodes may be required. Grounding is often confused with bonding, but they are distinct concepts with different purposes. Grounding refers to connecting electrical equipment and systems to the earth, while bonding refers to connecting different metal parts of the electrical system together to create a low impedance path for fault currents. Bonding helps to equalize the voltage potential between different metal parts, reducing the risk of electrical shock. Both grounding and bonding are essential for electrical safety and are required by the NEC. Bonding is achieved by using bonding jumpers, which are conductors that connect different metal parts of the electrical system together. Bonding jumpers must be sized appropriately based on the size of the circuit conductors as specified in the NEC. They must also be installed in a manner that ensures a low impedance path for fault current. Effective grounding and bonding are essential for protecting people and property from electrical hazards. By providing a low impedance path for fault currents, these measures help to ensure that overcurrent protective devices operate quickly and reliably, preventing electrical shock and fire hazards. Regular inspection and testing of grounding and bonding systems are recommended to ensure their effectiveness. The role of the neutral conductor is fundamentally to serve as a return path for electrical current in a single-phase or three-phase alternating current, also known as AC, circuit. In a typical 120/208 volt system, which is a three-phase, four-wire system, the neutral is derived from the center tap of the transformer's secondary winding. This configuration provides two voltage levels: firstly 120 volts between each phase conductor and the neutral conductor, and secondly 208 volts between any two phase conductors. The neutral conductor allows for the utilization of both voltage levels within the electrical system. When electrical loads are connected between a phase conductor and the neutral conductor carries the imbalanced current back to the source, which is the transformer. In a perfectly balanced three-phase system, the neutral conductor would ideally carry no current. However, in real-world scenarios, electrical loads are rarely perfectly balanced, and the neutral conductor carries the difference between the currents in the three phases. The size of the neutral conductor is determined by the expected maximum unbalanced load. The NEC provides guidelines for sizing the neutral conductor based on the type of load served and the harmonic content of the current. In some cases, the neutral conductor may be required to be larger than the phase conductors to accommodate nonlinear loads, such as electronic devices that generate harmonic currents. The neutral conductor must be properly insulated to prevent accidental contact with grounded metal parts. The insulation color for the neutral conductor is typically white or gray. It is important to note that the neutral conductor is a current-carrying conductor and should not be confused with the equipment grounding conductor, which is used for safety purposes. The equipment grounding conductor provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices to operate quickly and reliably. The neutral conductor is connected to the grounding electrode system at the service entrance, typically at the main service disconnect. This connection ensures that the neutral conductor is at or near ground potential, providing a reference point for the electrical system. It is essential to maintain a solid and reliable connection between the neutral conductor and the grounding electrode system to ensure proper system operation and safety. Improperly grounded or ungrounded neutral conductors can lead to voltage fluctuations, equipment malfunction, and increased risk of electrical shock. The relationship between the neutral and ground is critical for safety and proper operation. Bonding the neutral and ground at the service entrance creates a single point where both are connected to earth. This single point prevents circulating currents in the ground conductor, which can occur if the neutral and ground are bonded at multiple locations. Circulating currents on the ground conductor can cause nuisance tripping of ground fault circuit interrupters, also known as GFCIs, and can also create a shock hazard. The NEC specifies the requirements for bonding the neutral and ground at the service entrance. The bonding jumper must be sized appropriately based on the size of the service entrance conductors, as outlined in Table 250.102. C1 of the NEC. It must also be installed in a manner that ensures a low impedance path for fault currents. In summary, the neutral conductor serves as the return path for electrical current in AC circuits. It is derived from the center tap of the transformer's secondary winding and allows for the utilization of multiple voltage levels. The neutral conductor must be properly sized, insulated, and connected to the grounding electrode system at the service entrance. The bonding between the neutral and ground at the service entrance is critical for safety and proper system operation. Always consult with a qualified electrical professional to ensure compliance with all applicable codes and regulations. The NEC is updated regularly, so it is important to refer to the latest edition for the most current requirements. The specific installation mentioned is located in Bremerton, Washington. This geographic location does not significantly impact the general principles of grounding and bonding outlined in the NEC. However, local soil conditions can affect the effectiveness of ground rods. In areas with rocky or sandy soil, the resistance to ground may be higher, requiring the use of multiple ground rods or other grounding electrodes to achieve an adequate grounding resistance. Local codes and regulations may also have specific requirements for grounding and bonding that are more stringent than the NEC. It is important to check with the local electrical inspector to ensure compliance with all applicable codes and regulations. The climate in Bremerton, Washington, which is characterized by moderate rainfall and temperatures, does not typically pose any significant challenges to grounding and bonding systems. However, in areas with extreme weather conditions, such as heavy snowfall or prolonged periods of drought, additional precautions may be necessary to ensure the integrity of the grounding system. For example, in areas with heavy snowfall, ground rods may need to be installed deeper into the ground to prevent them from being affected by frost heave. In areas with prolonged periods of drought, the soil may become very dry, increasing the resistance to ground. In these cases, it may be necessary to supplement the ground rods with other grounding electrodes, such as a chemical ground rod, to maintain an adequate grounding resistance. The presence of underground utilities, such as water pipes or gas lines, can also affect the installation of ground rods. It is important to locate all underground utilities before driving ground rods to avoid damaging them. The NEC requires that ground rods be installed at least 6 feet away from underground gas piping. The proximity to saltwater or other corrosive environments can also impact the lifespan of ground rods and other grounding electrodes. In these environments, it may be necessary to use corrosion-resistant materials such as stainless steel or copper-clad steel to ensure the long-term effectiveness of the grounding system. Regular inspection and maintenance of grounding and bonding systems are essential to ensure their continued effectiveness. Ground rods should be inspected periodically for corrosion or damage, and the connections to the grounding electrode system should be checked for tightness and corrosion. The resistance to ground should also be tested periodically to ensure that it is within acceptable limits. In summary, while the geographic location of Bremerton, Washington, does not significantly impact the general principles of grounding and bonding outlined in the NEC, local soil conditions, codes and regulations, and environmental factors can affect the installation and maintenance of grounding systems. Always consult with a qualified electrical professional to ensure compliance with all applicable codes and regulations and to address any specific challenges posed by the local environment. Therefore, in conclusion, when feeding a panel from a 120/208 volt service, a 4-wire system with separate neutral and ground is generally required to ensure electrical safety in compliance with the NEC. The ground rod should be installed and bonded to the ground conductor to provide a low impedance path for fault currents. Consulting with a qualified electrician is always recommended to address specific installation requirements and local codes.